So we've learned a lot, actually, and it's only been like 3 weeks or something, right? We've basically derived all the equations that'll govern fluids and basically the equations that we'll use the rest of this term. We also covered a lot of math and a lot of the concepts that'll let us get there. Things like vector calculus, tensor calculus. Don't forget a lot of those things because we're going to be using them sort of throughout the whole term. Yesterday, we did one little tidbit of math on curvilinear coordinates. You guys have probably seen some of that stuff already, but I think it'll be useful, particularly for what we're going to be talking about for the next few lectures now, which is like actually solving flow problems. So the first one we're going to do is called annular flow. Okay, could you guys mute yourself? I think that's just you, Adrian. It's called annular flow. Okay, so picture this sort of idea. Let's say I'm trying to coat a wire. Okay, so I have, let's say, a tube full of fluid, and there's fluid that could potentially come in on the right-hand side of this. And through this little tube, I'm going to pull a smaller cylinder, specifically a wire. And that's going to go through in this direction with a speed of u. People in fluid mechanics really like to use u. I'm not sure why. Okay. So this wire kind of goes through the whole inside of this material. It's supposed to be symmetric. Sorry if I can't draw very well. Okay. And so this wire cylinder is being pulled through this larger cylinder at a speed of u. And there's fluid that just kind of naturally enters over here that then kind of coats the surface of the wire as it goes out, right? You can imagine like a copper wire or something, or a metal wire or something, and it's inside like a molten polymer solution or something like that. And then as you pull it out, then that polymer dries or solidifies or something on the surface of this material. Okay. And what we're going to try and figure out is basically, excuse me, the amount of fluid, for instance, the first thing we're going to do is trying to figure out the velocity profiles and stuff in here inside this larger cylinder, in between the larger cylinder and the smaller cylinder. But you can imagine that this sort of thing could be useful for understanding like how much fluid actually gets on the wire, how much polymer or how much of the plastic gets on the wire, depending on how fast you pull it, and the dimension of the system and stuff like that, right? Obviously, this is a really good candidate for cylindrical coordinates. So we have an r and a z in those dimensions, right? Let me assign more coordinates here, or assign more dimensions. I'm going to call this dimension here r, okay, big R. And then I'm going to call this dimension here, or I'm going to call the thickness of the wire. See where's the best place to draw this. I'll just draw it here. I'll call the radius of the wire right here. That's going to be called kappa times r. And so obviously kappa is going to be a parameter that varies between 0 and 1. When kappa is equal to 1, then the radius of the inner cylinder and the outer cylinder are the same. If kappa is 0, then the inner cylinder has 0 radius. Okay. Let me just write a few assumptions for this problem. I'll say both ends of the wire are open, or both ends of the cylinder are open. So in other words, they're at ambient pressure. So in other words, no pressure gradient. In Z. Okay. And we'll also say, just for simplicity, we'll neglect variations in Z. Okay. And so therefore no end effects. So you can imagine that the flow profiles might look a little different for the fluid entering over here and the fluid leaving over here. We'll say that this whole thing is that the length of this whole apparatus in the Z dimension is large enough that those things don't really matter. So no end effects, and then we'll assume steady state as well, okay? Or steady flow. So given those assumptions, we can anticipate that the flow field can just be something quite simple. It's just going to be Vz as a function of R, right? Because there's no variation in z, and so Vz can't be a function of z. And then we expect that there's not going to be any flow in the R direction either, that the flow is only going to be moving in the z direction. Okay? In other words, Vr and V theta are all equal to 0. Okay? And then we can look at our Navier-Stokes equations now, right? There's 4 of those equations. One of those is continuity. We don't need to worry about continuity in this case. You'll find that over the next few lectures, we're going to be talking a lot about unidirectional flow situations, basically where the flow only goes in one direction, basically only goes in, for instance, in this case, the z direction. In that case, a lot of times the continuity equation doesn't really matter because in continuity it says dvz dz plus dvr dr plus dv theta d theta. That's if this were Cartesian coordinates, there's all these other prefactors that come in when you have cylindrical coordinates, but let's not worry about that for a second. In that continuity equation, only one of the terms is equal to 0, is non-zero. And so there's not really any action going on in the equation. So it's automatically satisfied, basically. Okay. There's also 3 components in the Navier-Stokes equations. We don't really care about the R component, and we also don't care about the theta component, right? And so what I'll say is that the Z component of Navier-Stokes matters, okay? And that equation is this. Okay. I'm simplifying a big chunk of this math here. Right, if you remember, I can page back if you want and look at the actual Navier-Stokes equation in the z direction. It's really complicated. But with all these different assumptions, we were able to eliminate most of those terms. And I think you guys have done enough engineering problems and stuff that you kind of know how to get rid of several of those terms. For instance, steady means that all the time derivatives are 0. These all being 0 allows us to kill a lot of those components. No pressure gradient in z, that allows us to get rid of the pressure. And so we end up with only one remaining term. Okay. Based on this one remaining term, there's going to be 2 boundary conditions because there's 2 derivatives in R, right? So that was step 2 in our analysis method, right? And those 2 boundary conditions are basically just the no-slip boundary condition at the 2 surfaces, right? That's that Vz is equal to 0 at R equals R, okay? Basically, this is the outer surface, and the outer surface is not moving. And so at R equals big R, Vz is equal to 0. Okay. And then we also have a second boundary condition. We'll call that BC2, and that's that Vz is equal to U at R equals kappa R. Okay, kind of makes sense. That's just because the inner cylinder is being drawn to the right at a speed of U. Okay, and so this is fairly simple. I think most of us can solve this at this point. Let me just go ahead and do that together real quick. So to solve, we're just going to integrate this guy twice. So first, we can basically get rid of, excuse me, we'll get rid of this stuff in the front because that's all. We can just divide 0 divided by all of that. It's just the same. So we get, whoops, sorry. D by dr of Vz over dr is equal to 0. Okay, that implies that we integrate once, we get R dvz dr equals C1, some sort of integration constant, right? We can divide by R and then integrate again. So let's go ahead and divide by R. dvz dr equals C1 over R.
Hey, Professor, we can't hear you.
People hear me now? I don't know how this thing eats battery so quickly. It's really weird. I'll point out that Caleb sitting in class was able to hear me the entire time. Where did I cut out?
About the start of BC1,
About
that
the
line.
start of BC1. Okay, it should be pretty self-evident from what I wrote, though. Basically, I just applied BC1, and so 0 goes here, and then big R goes here, right? Same thing for BC2. U goes here, and then kappa R goes here. Okay, and then you just solve these two. This is a linear system of two equations for two unknowns. And that gives us what our two unknowns are going to be. C1 is just U over log of kappa. And C2 is equal to minus U over log of kappa times log of R. I'm skipping a lot of steps here just because you guys don't really care about me doing lots of algebra in front of you. I've done this problem before. I'm pretty sure the math checks out. If it doesn't, please let me know ASAP. Okay? And so then the actual solution is just that Vz is equal to U over log of kappa times log of little r over big R. Okay, fairly straightforward. Now, typically in this class, once I ask you for the velocity profile, that's usually not going to be enough. We're going to ask you to analyze it or think about the different implications and stuff like that. And so as I mentioned, in this particular application, we're talking about, sorry, I'll page down in just a second in case you haven't copied it down. But we're talking about potentially using this to coat a copper wire or something as I pull it through or something like that, right? And so in order to do that, we might care about the actual volumetric flow rate of something of this fluid moving through that space between the cylinders, but the annulus. And so the volumetric flow rate looks like this. That's just the integral of the flux or of the velocity through some surface. In this particular case, that surface looks like this. Okay. I think we all understand this, this integral from 0 to 2 pi. I'm just integrating over all the angles, right? And I'm integrating from radii in between the two cylinders from kappa r at the lower limit to r at the upper limit. Okay, so it's just a matter of plugging in what we solved up here to get what we to get our flow rate. So I'll take out the 2 pi from the theta integral, and then take our other constants out front. And then evaluating that. Okay. You're going to need to know a little bit of integration by parts in order to do that integral. One thing that does make this a little bit easier is this. This is just a rule of logs, right? But this little bit in front here makes you do, does imply that you need to do integration by parts. If you don't know how to do that, please go back and refresh yourself. In fact, maybe I should throw something on the homework about that, because we're going to start using integration by parts a lot in the next few lectures. Okay, but that's not that mathematically interesting right now. I'm just going to go ahead and write the answer. The answer looks like this. In case there's any ambiguity, everything in here is actually kappa. I'm not trying to write I'm not trying to write R at all in these. This is kappa in here. Okay. And let's just give ourselves a little bit of a sanity check. Okay. The units here actually do kind of work out. Kappa is unitless, right? And so, for instance, we're taking a log of kappa. That's okay. It's unitless. Everything in here is actually unitless. We'll plot that in just a second. Okay. The volumetric flow rate here actually does kind of work out too. This is an area pi radius squared. It's actually just the area of the outer cylinder. Okay. And then U is a flow rate, or U is a velocity. And so what I have here is then just a like a velocity per, a volume per second or something like that. Okay. In fact, let me actually take this guy right here, and I'll call this F of kappa. I'm just going to sketch what that looks like. This is something that's non-dimensional. You can imagine if I were to plot that a really convenient way of plotting this, if I were to like trying to make this universal for anyone who would care about a problem like this, will be to plot my F of kappa. Or another way of writing this is basically a rescaled volumetric flow rate, right? Versus kappa. Okay. I'm not going to pull up MATLAB. Later on, at some point in the class, for things that are more complicated, I'll pull up MATLAB and show you what it actually looks like. You'll just have to trust me that this particular solution looks something like this. Okay. You know, you can pull up MATLAB and plot this. This is not going to be difficult. Okay, or you can anything that you like to use to plot these sorts of solutions. Okay, and so this sort of solution hopefully should not be surprising. Let's look at the various limits. Okay, this particular limit right here, when kappa equals 1, can people kind of visualize what that would look like in this case? In this particular case, when kappa equals 1, just anyone unmute yourself. What does that correspond to then?
It's just when the wire is just as big as the cylinder it's in.
Right, exactly. There's just no gap in between the two cylinders, right? And so if there's no gap, then obviously there's no flow rate. And that's why the flow rate goes down to 0 over here, okay? Someone else for the other limit, when kappa goes to 0, then does that kind of make sense why the flow rate would go down to 0? Someone else, not AJ. Any ideas for why that would be the case?
Then you have no wire pulling anything.
Yeah, there's no wire pulling anything. You still have a wire pulling on it, and it's still moving at a velocity u, but the surface area is now 0, right? And so the perturbation of that wire onto the non-moving fluid is essentially 0, and so you have essentially no flow rate as well. And so if you wanted to, for instance, get the most optimum, or like you wanted the thickest coating on the wire as you can, then you would pick a kappa value that's here, right? That's how you would design a process like this, for instance, right? It is also really useful to look at limiting cases of problems. Let's say that our problem was not quite so easy to solve here, where we could just integrate a couple of times and then plug in boundary conditions and get it, and then actually write down our solution, right? Then it might be helpful to approximate a few different things. And we're going to get into that a lot later, but this gives you a little bit of a preview. Let's, for instance, look at what happens in the limit when kappa approaches 1. Okay, let me go ahead and draw that. I'll try at least. Here's our outer cylinder. Okay, and let's say our inner cylinder is now almost the size of this outer cylinder. Okay, here's my axes here. Z, and R. All right. So in this case, do we have just some sort of hypothesis for what might happen? You might think that the gap here can get really, really small, right? And so if the gap between these two cylinders is really small, then maybe it doesn't really make quite so much sense to think about our axes, our coordinate axes, as R and Z in this case, because the R is always going to be either 0.9999 or 1, right? And so it doesn't really make sense to define our R in that regard, right? Perhaps it then makes more sense to define a new set of axes. I'll say a y that starts right there. Okay, and y starts at the outer surface and increases as I move inward. Okay, and also we will let some sort of epsilon equal 1 minus kappa. Okay, and so that means, so kappa goes to 1 implies epsilon goes to 0. Okay, and then as I mentioned, we're going to redefine our axes here. We'll define y as big R minus little r. Okay. Now, in this case, we actually know what our solution is, so we're going to cheat a little bit. The full way of doing this is to actually apply this sort of approximation to the full Navier-Stokes equations and then try and solve it in that way. And I'll tell you a little bit later on in class how we're going to do those sorts of approaches. But in this case, we can cheat, and so let's go ahead and do that. We know from our analysis above that the solution looks like this. Okay, but now we can write all this in terms of epsilon and y. Okay, so we have little r is r minus y. Okay, and kappa is 1 minus epsilon. Okay, or just another way of writing this is this. And now we can use a Taylor series to actually simplify this a little bit. Okay, the log of 1 minus x in a Taylor series can be approximated. That should be a 2, sorry. Can be approximated like this. And when we know that y over big R is small, and when epsilon is small, then we can just use the first term of the Taylor series. And so we get that Vz over u is equal to minus y over r over minus epsilon plus all this other stuff in the Taylor series. Okay, that kind of makes sense? And so that allows us to write y over, whoops, one minus kappa times r. Okay. This is actually a pretty familiar solution or fluid solution to you guys. To make it look even more familiar, I'm going to define a new variable here. This thickness right here, I'm going to call h now, right? And that thickness h is exactly defined as epsilon times r, right? Or 1 minus kappa times r, right? Just geometrically, that works out. And so this is just y over h. Okay. To make it even more familiar for you guys, this flow profile looks like this. Does that look familiar? We haven't explicitly covered this flow profile in class, but we've referenced it a couple of times, right? Does this, what do you guys think this corresponds to? This is just a linear flow profile, right? That goes from 0 when y is equal to 0 to u when y is equal to h, right? Can anyone sort of name what this flow profile might be or sort of visualize what this would be? Okay, if I have no takers, I'm just going to start drawing. This is flow between two parallel plates, where the top plate moves at a speed of u. I have an axis y increasing in this direction. The thickness of the fluid between these two plates is h, and the flow looks something like this. You can call this simple shear if you want, right? This is also, people like to call this simple shear or flow between two plates. Right? It's just a linear increasing velocity profile like this. Looking back with hindsight, if I were to take this annular flow profile, or if I were to take this annular flow situation and allow the kappa to approach 1, in other words, get to this situation like this is maybe exactly what you guys would have expected, right? We're seeing essentially no curvature now because we're sort of so close to the surface at this point that we're not even detecting the curvature of the cylinder anymore, right? And so what we basically have is this inner cylinder corresponds to this top parallel plate, and this outer cylinder corresponds to this bottom parallel plate that's not moving. And the curvature is gone in the same way that when you're standing on the surface of the Earth, you don't notice the curvature of the Earth either, right? Now, the curvature stuff actually does come in a little bit more if we start throwing in these higher order terms in the Taylor series, but we don't have to deal with that because we're letting kappa go to 1 or epsilon go to 0. Okay, does that all kind of make sense? Okay. That's all I wanted to say so far on the annular flow problem. I'll do one more really simple flow problem, and I know you guys have seen this, even though this simple shear problem, even though we haven't explicitly covered it, but this is a graduate level class, and so there's no reason for me to cover it. The one thing that I will mention, that I will try and cover, just because we can't really do a fluid mechanics class without you guys having at least, or at least me being able to say that we have covered this, is just pipe flow, right? I'm going to do this really, really quickly because just give me a nod or shake of your head if you've actually seen this problem done before. Okay, I'm seeing mostly nods and very few head shakes, and so I'm just going to do it really, really quickly, basically. Partly also because we might build upon this problem a little bit later in class. We have a pipe that has a radius of r, and we have fluid flowing in this direction. That's driven by, I won't actually draw the flow profile here, but it's driven by some sort of pressure gradient in the z direction, right? So we have r and 0. Again, we can anticipate here a flow field that looks like Vz as a function of r, and then no flow in the r or theta directions. Okay. For this one, let me just go ahead and write out some of the other components of the Navier-Stokes equation. We have the r component of the Navier-Stokes equation that reduces down to something like this. Okay, and we have the theta component of the Navier-Stokes that reduces down to something like this. This is the curly P that takes into account the body forces and stuff. hopefully it shouldn't be too foreign to most of you guys. The z component of Navier-Stokes is the one where all the action is, because that's the direction that the fluid is flowing. That looks something like this. Okay. And then in this particular equation, we know that dp dz is not a function of r. And so we can integrate it, right? We need two boundary conditions in order to do that. The two boundary conditions typically in this case are that Vz equals 0 at r equals big R. And then the second boundary condition is typically something at Vz at r equals 0. Usually we call this either a symmetry condition or a no stress condition, where or we say that Vz is finite or whatever at r equals 0. Okay. And then it's just a matter of taking this particular equation, integrating it twice, applying these two boundary conditions, and then getting the answer. Okay. I won't do that, the math here, because again, you guys have probably seen this, and I'm seeing a couple yawns at this point. Okay, so I'll just say integrate, apply boundary conditions, and what you get is that Vz is equal to 1 over 4 mu times the pressure gradient. That. Okay. That flow profile looks something like this. It's parabolic. Okay, it's higher in the middle than it is on the outside. That's just because this dp dz is typically negative. It's higher pressure over here than it is over here. Okay, and then of course you can also look at the volumetric flow rate. Volumetric flow rate is the same as the example that we had above. Like that. And we can integrate this, and we get something that looks like this. Okay, and this is the Hagen-Poiseuille's law, right? All right. Any questions on this? This took like 5 minutes, right? I went through this intentionally fast because, again, this is a graduate level class, and I think all of you guys have already seen this before. Cool. And so now we have a little bit of experience with flow problems and stuff like that. Now we can go into things that are a little bit more complicated and perhaps a little bit more interesting. Okay. I can give myself a new section. What we're going to talk about now is a pretty famous problem. It's called Stokes' first problem. It's going to look a little different than the two relatively simple problems that we had talked about earlier. Let's say we have a plate with fluid above it. Give myself a set of axes here, x and y, like that. And we'll say that the plate is suddenly set into motion at time t equals 0 towards the right. Okay, so the flat plate suddenly set in motion. Okay. And so sometimes it's actually easier to define this problem by actually writing down our boundary conditions. Okay. Basically what we have is that we have fluid that's defined for values of positive y, where our velocity, which is moving in the x direction, which is only moving in the x direction, is equal to 0 at t equals 0. for all positive y's. Okay. And then we have from a no slip boundary condition that the velocity is suddenly pulled to the right, or the velocity of the plate is suddenly pulled to the right at a speed of u for all t greater than 0. Okay? And then this velocity, and then the fluid extends all the way out to the sky, to as far as you want, throughout this material. And so the way we'll define that is that we'll say that velocity is equal to 0 for all time as y goes to infinity. In other words, there's still fluid everywhere, but as you get farther and farther and farther away, then you're eventually just going to reach 0, because you're not going to feel the effects of this fluid. Okay. We'll have the usual assumptions that we had earlier. We'll assume that Vx is a function of y and time. Vy and Vz are both equal to 0, so we have flow only in the x direction. And we have no pressure gradient. Anywhere in our problem. Okay. Some of you guys have probably seen similar problems at some point, if not in a fluid mechanics class, but in other classes. We'll get into that in just a few minutes here. But one thing that I'll just point out is that the way that this problem is different than the other two problems that we've dealt with so far is that my velocity here is a function of both y and t. Right? And so that's a little different. That means that our equation here is going to have derivatives in both y and t. And we have to figure out how to solve equations that look like that. So for the next roughly week, maybe a little bit longer, we're going to be talking about how we're going to solve equations like that. Okay? We only have flow in the x direction, so it's only the x component of the Navier-Stokes that matters here. So I'm playing fast and loose with the 6-step plan for success in fluid mechanics, but you guys kind of see the drift here. Once we've done this sort of long enough, you sort of see how these problems are typically set up. Okay, but the Navier-Stokes equation now, using these various assumptions, gets reduced down to something like this, right? Where it's not that it's unsteady, and so we need to keep this time derivative. But the fact that it's unidirectional, there's no y or z component, and that Vx is not a function of anything besides y and t allows us to eliminate most of the other things except for this particular term. We typically simplify this equation even further by just combining our mu and rho into a kinematic viscosity. And we have an equation that looks like this. Okay. Let me write that better, sorry. It's called a kinematic viscosity. Okay, and let me just write some, I'll rewrite these boundary conditions a little bit and actually give them a name. I'll call this initial condition, or I'll call this thing here an initial condition. This is Vx is equal to 0, at t is equal to 0, y is greater than 0. And I'll have two boundary conditions here. Vx is equal to u, at t is greater than 0, y is equal to 0. And then another boundary condition, Bc2, Vx is equal to 0, at t is greater than 0, y goes to infinity. Just to check really quick, again, for every derivative, we need to make sure there's one boundary condition. So here we have one derivative in time, and so we have one boundary condition defined at some time, t equals 0. Then we have two boundary conditions for y, because we have two derivatives. One of those is defined at y equals 0, another one's defined at y equals infinity. Okay, this is a pretty famous problem in fluid mechanics. As I mentioned, some of you guys might have seen this problem before if perhaps you've taken a class that I've taught here at Northwestern, heat transfer. If not, perhaps you guys have seen this in other heat and mass classes and stuff before, or maybe even your undergrad fluids class covered something that looks like this. Okay, the analogies in heat and mass transfer look like this. There's a pretty well-known problem in heat transfer called basically transient heat conduction into a semi-infinite slab. Okay. You can imagine, for instance, like a really thick piece of material, and then the surface is suddenly changed to some other temperature. That's not the same temperature as it was initially, right? In heat transfer, again, this is not a heat and mass transfer class. You might cover something like this later on in next term when you, some of you guys are going to take heat and mass transfer with Professor Richards. What you'll find is that the math looks something like this. Okay, where this alpha can be defined in terms of thermal conductivities and heat capacities and stuff like that. This alpha is called a thermal diffusivity. Okay. You can imagine then something similar in a mass transfer class. In a mass transfer class, we have a problem called transient diffusion. Again, into a semi-infinite medium. Okay. There, the way that you think about it is that the concentration rather than the temperature is also governed by an equation that might look something like this, where now this D here is just the diffusivity of the species. The reason why I wrote this math down, again, we have not and will not derive these sorts of equations in this class. The derivations actually don't look all that different. It's all about just conservation laws and stuff, right? But you can kind of see how these two equations right here look very similar to this, right? And if you've seen how these equations are solved in these other classes, then the solution here is just going to look very, very, very similar. Okay. In all three different cases, you can see that you have some derivatives with respect to of whatever property you care about. Here it's velocity, here it's temperature, here it's concentration. The units on both sides of these derivatives actually cancel out, and so there's a velocity here and there's a velocity here. Temperature here, concentration here, right? But based on the denominator of these derivatives, the units of nu, alpha, and d are all the same, right? By analogy to these sorts of things, this guy here is a thermal diffusivity, so basically how quickly temperature diffuses in our material. This D here is, well, it's actually diffusivity, so it's basically how quickly our concentration or our particular species diffuses in our material. Okay. And so nu then in fluids is basically can be thought of as the diffusivity of whatever species is actually moving in this case, and that's momentum. Okay. And again, the units are the same as those units of everything else that we've seen of all these other analogies, and that's L squared over time, length squared over time. Okay. Okay. To solve this particular problem, we're going to use a pretty well-known method called a similarity solution. Let me write this better. Similarity solution. Okay. The way we do this is we're going to define some non-dimensional f as my Vx as a function of y and t divided by my u. Okay, that allows us our equations to now be reduced to df dt times nu. You can see how this equation up here, all I'm doing is just dividing by a u on both sides and then getting something like this, right? And then our boundary conditions can now be defined as something like this. Basically, if Vx goes to 0, then f also goes to 0. Whoops. Okay, and then if Vx equals u, then f equals 1. And again, if Vx equals 0, then f equals 0. Okay. It turns out that while we know what the units of f is at this point, it's just a velocity over velocity, and so it's non-dimensional, right? It has no units, right? Because f has no units, then it also must depend on something, on some other quantity that also has no units, okay? But of course, y and t do have units, right? My f here has to be a function of both y and t. Y has units of length, and t has units of time, right? And so perhaps then, my f then should depend on some combination of length and time to give me something that has no units. Does that kind of make sense? So let me write that down while you guys think about that. Okay. So f is dimensionless. Okay. And so it can be written in terms of other dimensionless variables. Okay. But unfortunately, all the other variables in our system here do have units. Again, t has units of time, y has units of length. But it turns out our nu here, this kinematic viscosity, has units of length squared over time. Okay? And so perhaps what we'll note is that one combination of y, t, and nu has no units. That combination looks like this. Y squared over nu t. These units all exactly cancel each other out. This nu here has units of length squared over time. That length squared cancels with this length squared, and the time cancels with this time, right? And so perhaps the right thing to do is to try and express our equation here, f, as a function of this combination of variables. This is going to be called a similarity variable. Actually, the right, or the mathematically, the easier thing to do is we'll let some sort of Greek letter xi here, that's how I write xi, it's just some sort of a large amount of squigglies, is going to be defined as y over the square root of 4 nu t. 4 doesn't matter, it's just an order 1 constant, also dimensionless, right? Okay. And we'll say try to only allow f to depend on y and t through xi here. Okay. Okay, I have just a few more minutes. I guess I'll talk a little bit. I'll talk very briefly about how to actually make this f depend on y and t. It's just an application of the chain rule. Here's what I mean when I say that. If I care about this derivative df dt, right, then another way of writing this derivative is df dxc times dxc dt. Okay. And because we know how C depends on T, then we can just write this guy out here, right? And so this is just equal to df dc times, well, derivative of this with respect to time, right? Bear with me for a second. That derivative looks something like this. Okay, maybe you guys can believe me real quick, but very quickly, the y doesn't change. This is 4 nu t to the power of -1/2, and so the -1/2 comes out in front here, and then the power becomes -3/2. I have to chain rule again because there's a 4 nu, and that 4 nu comes out in front over here, right? And so I get something that looks like this. Okay, just through some simplifications. I can do something similar for the other expression of my derivative, d squared f dy squared. I have to do that twice because this is a second derivative, and I only know how to do chain rule on first derivatives. So df dy looks like df dc times dc dy. Okay, and so it's just a matter of taking the derivative of this with respect to y. That's relatively easy. It's just a factor of 4 nu t on the bottom. So this gives me 4 nu t to the 1/2 power to the -1/2 power times df dc. Okay, and then by analogy then, d squared f dy squared is just one more power of this. Okay, it's just applying the chain rule again on this guy here. Okay, and so that's 4 nu t to the power of -1 d squared f dc squared. Okay. And the last thing I'll do is just I'll mention that what I'll start off with tomorrow or on Friday is basically that now I have an expression for df dt. It's this guy right here. I have another expression for d squared f dy. That's this guy right here. And so I can plug those directly into my partial differential equation and then see where that actually takes me in solving this. Okay? All right, any questions at all about this? We'll pick up right here when we reconvene again on Friday.
How do you get the root 4? Like, how do you get the root 4?
Where did the
instead
4
of
come
just
from?
Y squared, yeah.
Yeah, because I peeked at the answer at the end.
Aha.
That's actually why. You could do the whole analysis without having the 4 in there. You just find that having the 4 in there just makes it slightly easier.
That makes sense.
Mm-hmm. Okay, any other questions? All right, if not, I'll see you guys on Friday.
Thanks.